I'd like to introduce our next keynote. Albert Ilkabar is General Manager of Data Center Memory and Storage Solutions, Vice President Data Center Group at Intel, where he led the introduction of the world's first persistent memory to market in 2018, a milestone achievement for our industry. Before taking on his position, he oversaw the commercialization of new non-volatile, high-performance memory technology at Matrix Semiconductor and SanDisk, as well as holding design engineering and management roles in Intel's microprocessor division. A 27-year veteran of the semiconductor industry, he earned his master's electrical engineering from University of Michigan and an MBA from the Wharton School of Business, University of Pennsylvania. He holds over 50 patents in semiconductor process, device design, testing, and has published multiple journal papers at multiple conferences. Now, on a little side note, those of you who are sports fans will know University of Michigan's stadium is nicknamed, anyone? Big House. Exactly. It's the largest stadium in the United States and the second largest stadium in the world, and has hosted crowds in excess of 115,000. And I just found out this morning that Alper's son or daughter is at University of Michigan, so he's probably going to have many visits to the Big House. Today's topic is about a significant advancement in memory technology. The talk is called Breakthrough Data-Centric Computing with a New Memory Tier. Ladies and gentlemen, please welcome Albert Ilkabar.
Thank you, Jay. Good morning. On April 2nd, we launched Optane DC persistent memory. I've been coming to this summit for many, many years now, and every year I came here, the stuff I was working on would always be covered under emerging technologies. Year after year, emerging and emerging and emerging. So finally, with this in my hand, I think I can declare we have emerged. Thank you. For me, the journey started in 2000 here in the memory industry. In 2001, I joined Matrix Semiconductor working on 3D cross-point memory technologies. So it's been more than 18 years now that today here, I have the distinct honor and privilege to share with you the culmination of work of hundreds of Intel's employees over more than a decade. But also for those of you who are working on some obscure technology where it just looks like it's never going to happen, I ask that you please continue working. And I look forward to seeing you here very soon as well. The other point I want to make sure that I acknowledge is that as we are hitting this important milestone in our industry, we at Intel couldn't have done that with the many contributions of our partners, of our customers, and many of you in this room who are contributing to the persistent memory technology and what I call the persistent memory revolution. I was very pleased to see coming in here that actually now there are tracks on the Memory Summit covering memory, persistent memory. It's not called emerging memory anymore. There is new memory technologies, and 3D crosspoint is mentioned under that. So I really want to thank all of you from the bottom of my heart for making this happen with all of us. So thank you so much. The persistent memory is a new tier, a new category in the memory storage hierarchy. So we historically have shown this memory storage hierarchy as a pyramid, and many people think of the memory and storage, that hierarchy, as a continuum of devices of various characteristics. But if you really think about it from the perspective of software and applications, how they use these different technologies, storage and memory are very distinct beasts. An application accesses memory through load store instructions, and the CPU just essentially doesn't have any involvement of the software and will access memory through a low latency, high bandwidth interface. And it's going to have a memory addressable memory technology attached to it with latencies measured in nanoseconds, and it's going to be volatile. When it comes to storage, however, the application, when it wants to go storage and has to do an I/O cycle, it's going to drop whatever it's doing. It's going to do a context switch and start running a kernel code, a device driver probably, and going to spend microseconds probably getting to that device that's going to be many microseconds or milliseconds away. It's going to be a block device, but you get persistence and storage with that. Now, the persistent memory tier that we are introducing now closes the gap between memory and storage. And the device exhibits behaviors of both memory and storage. First of all, as the name suggests, it's a memory device. It sits on the low latency, high bandwidth DDR bus along with DRAM. It's byte addressable. It's very low latency. And just like storage, it also happens to be persistent thanks to the 3D crosspoint technology we use in building it. So you really see characteristics of both storage and memory in one tier. So this is pretty new. In this talk, what I wanted to do is really not talk about the design and characteristics and features of the product and the many applications and customer testimonials. But what I wanted to do is really look at persistent memory in the context of storage, in the context of memory, and also how one possibly could really re-architect or rethink the whole memory and storage concepts to come up with breakthrough performance in the memory compute. And the intent here is really to stimulate thought and so that we can collectively start innovating and come up with great ideas to meet our customers' needs. So with that, I'm going to start in the persistent memory as a storage. Now, let's start looking at the performance of the device. I like to look at this kind of a graph that shows a latency of a given technology as a function of bandwidth you run. This specific graph that you're looking at looks at three storage devices from Intel. At the top in green color, you see an NVMe SSD with 3D NAND. In the middle, you see an Intel Optane SSD. And at the bottom, what you see is the Intel Optane DC persistent memory. The x-axis shows the bandwidth we run into this device. And in the y-axis, in a logarithm scale, you're seeing the latency associated with that. We are running a 70-30 read-write mix of random I/O into these devices and see how their latency varies as we run traffic into it. The first thing you're going to see is that compared to a NAND SSD, Optane persistent memory delivers up to 3.7 times higher bandwidth, which is pretty amazing, but what really surprises a lot of people is the latency improvement. When you look at the data right around a gigabyte per second, a pretty modest bandwidth traffic, you're going to see that we're delivering just about 1,000 times improvement in latency. This is an incredible improvement in latency. So the real question is, how do you take these device-level characteristics and convert them into applications that our customers can really benefit from? So a couple of examples I want to go through. The first one is looking at an application, a workload, a database called Cassandra. Who here uses Cassandra? Okay, few people. Who here has an iPhone? Who here is a Netflix customer? So you all are using Cassandra every day. So Cassandra is actually a massively scalable, very popular database that many cloud service providers use. And typically, the way the requirements for this application are given is SLAs for meeting number of requests that customers are going to put out and meeting certain response time for that. And that response time turns out to be limited by the number of updates per transaction each server can make, and that's limited by the storage bandwidth. Now, what we have done is we have gone in and replaced NVMe drives in a server with Optane DC persistent memory, and we optimized the storage engine in Cassandra and looked at the results. What we are seeing is an average update transaction throughput improvement of 7x with a new system. But when you looked at the number of systems we can support in each system, it went up by 9x due to very low variability in our response times and the very small tail we have in our responses. So what that means for our customers is that they can achieve the same customer footprint and support the same customer footprint with 1/9 the number of servers. That means that you're going to have 1/9 the hardware expenses. That means that you're going to be spending a lot less on your OpEx energy. And in the case of a large scale-out deployment, this meant that the next data center that had to be built didn't have to be built anymore. So this is hugely, hugely important. Another nifty feature of persistent memory as a storage device is the ability to do RDMA replication. Replication is a critical piece of any enterprise storage subsystem that requires high availability, and a lot of times the performance of that subsystem tends to be limited by the replication speed. In a traditional system, the way replication would happen is the CPU would essentially copy the data from the storage into the DRAM of the system, then shoot it over to the next system, and the second CPU would grab that data and put it back into their storage. So there's a lot of CPU involvement running code, and you're essentially spending time moving data about. With persistent memory, because it is a memory device, you can avoid all of that and simply run an RDMA cycle. The CPU doesn't have to be involved at all. What that really means in terms of performance is, and this is a measurement that we have performed, you're essentially avoiding all the software stack, and all you need to do is just push the data through a network, and very fast devices are going to capture the data on the other side of the network. So this meant that we could actually achieve 14 times faster replication latencies. Now, how does this get converted to a real-life application? So we have today the privilege of sharing the preview of Exadata, and courtesy of our friends at Oracle. Exadata is the premium flagship engineered solutions product from Oracle, optimized for very high performance database applications. Oracle's mandate for Oracle, the Exadata design, is achieving world's highest performance, highest availability, as well as best performance per cost. And our friends at Oracle have used persistent memory in their storage subsystem, and they are essentially using the persistent memory as a shared cache layer and running RDMA to capture log writes and improving their overall performance by 10x. So this is ability to take a very high-end system, which is at the frontier of what our industry can achieve today. And with this new technology, we're able to push the frontiers of performance by an order of magnitude, which is pretty amazing. So I'm really looking forward to seeing actually the introduction of this product very soon, and also hoping that we're going to see even more impressive numbers than what we're getting here. Next, I'm going to start talking about persistent memory as a main memory in the system. So in the past presentations, we've gone through many applications where we have used Optane persistent memory as a main memory in the system. We've shown how well they behave and how we can do all of that. Rather than going into that, what I wanted to do here today is actually see if we could sort of create a framework where we can think about, given different resources in the system, how would you optimize a system design? And how would you make the trade-offs between cost and cost and performance? And one of the work that we have seen that really impressed us is work by David Lomé at Microsoft. And he had an idea, and we really liked that, and we wanted to expand on that. The concept goes something like this. When you have a given technology, and you're going to get performance out of that, there is two costs associated with that. The first one is the storage cost, and the second one is the performance cost. The storage cost is how much you pay for the media to hold your data. If you happen to have 1 terabyte of data, and you decide to put that in DRAM, so the storage cost happens to be what you're paying for 1 terabyte of DRAM. The performance cost though is associated with the system resources you're consuming to get incremental performance. Typically, if you want to get more performance out of the system, you're going to put more resources, you're going to deploy more cores, more memory, et cetera, and they all cost. And the concept here is sort of the cost that an infrastructure as a service provider will be charging you for those type of resources. So we've taken this concept and looked at how data really looks. Now, here is our data. Although these pictures, the graph looks like they're just random lines, they happen to be real data that we measured. And the way we have done is we've taken essentially different media and looked at their performance, and also we containerized the system resources and applied more and more containers to get more and more performance out of the system. So what I'm showing here is two graphs. In blue, you're seeing running data out of an NVMe NAND SSD, and the red one is the main memory. So essentially, what you're seeing is and you can see that the performance of the storage is so slow that any meaningful performance you want to get out of it, you're immediately going to have to switch to DRAM. So it's not a very viable way of designing a system. But by the way, nobody does this. Nobody really runs their data out of SSDs directly out of storage. Instead, what we tend to do is use a combination of SSDs and main memory in a cached architecture. This is what a lot of databases do today, like Microsoft SQL and Oracle, et cetera. Many architectures are like this. So the second line that I'm showing that sort of shifted and improved the cost performance curve for that architecture, we made an assumption there. We're showing a line that represents a cache that essentially holds roughly 10% of the data and has a hit rate of about 90%, which means like 9 out of 10 I/O requests, you essentially find the data that you're looking for in the fast cache tier, which is DRAM. So as you can see, having this combination of a cached architecture with these storage device and the DRAM, the optimum design would follow the yellow line, right? Essentially, at any given point, you're trying to optimize cost for a given performance target. As you will see, in the lower parts of that performance, you're going to be using that cache architecture, your SSD, and then a little bit of DRAM. But then if you want to go really to higher performance levels, you have to switch to the red line, and that's going to be putting the data in the DRAM. This is sort of what in-memory databases, in-memory analytics frameworks, et cetera, tend to do, right? If you really want that performance, you end up going to that red line. Now, given this concept, we wanted to see, okay, how does persistent memory change this framework, or how do we evaluate that in this context? Because that's going to be a really interesting question. So here is the green line, and that's essentially, again, data collected on our system, test system, that's showing how the opt-in DC persistent memory behaves. And you will see here that actually with this new paradigm, you're able to cover very large portions, regions of the performance tier with persistent memory. And that allows us to actually use a very small amount of cache tier in DRAM and get significant performance improvements at much lower cost points. So a great example, and we have many examples of applications that are optimized for opt-in persistent memory. in memory databases like Redis and Aerospike and analytics like Spark that they are doing in memory. We've done all that work and we've shared that in the past, and they're available to you if you're interested. But I want to talk about specifically about how SAP HANA has implemented DC persistent memory, because they have been very public about their architecture. So what they showed is that when they use persistent memory, they're able to use DRAM for their small volatile data structures, and they're using their column store main, which is the name for the trunk of the database, and holds about 95% of the data in the persistent memory. So essentially, significantly, persistent memory heavy system. So with that, they were able to achieve really results that were very close to the DRAM-only system. And in this case, we have some public benchmark results, and that's showing a system from HPE that achieved almost 95% parity with DRAM. Now, you're getting significant TCO savings by using persistent memory. You're getting significantly more capacity that you didn't get before. And on top of that, you also have the improvement of restart times. In these large systems, if the system goes down, restarting that system sometimes takes 4 hours. And that's very disruptive to the business continuity and a major pain point for our customers. By using DC persistent memory, they can restart their system 12.5 times faster than before and just create a significant improvement in their system availability. As I mentioned before, SAP is not the only partner ISV we have in our ecosystem. This is a vibrant and developing and growing software ecosystem. So as you come and work in the persistent memory world, you're going to find even more people interested in developing software and optimizing software. This takes a lot of time. It's a slow process, but there's already a lot of people who have all the way from operating systems to foundational infrastructure and storage software to data access layers like databases and analytics frameworks, which many of the business applications use their base, are being right now transferred and optimized for optimum persistent memory. So this is a fantastic list of partners that we have in our ecosystem. Next and finally, what I want to touch on is, so we've looked at storage, persistent memory in storage. We looked at memory and persistent memory in there. But we also started working on a solution where we're rethinking the entire memory and storage hierarchy and thinking about how we can optimize pieces and not just confine to a single server, but we're rethinking the entire rack. How would one take advantage of this new technology? The solution our team is working on is called Intel Data Management Platform, and it's a rack-level solution and consists of compute nodes, storage nodes, and infrastructure nodes. What we have done is decked our compute nodes with up to 6 terabytes of Intel Optane persistent memory, and the software was configured such that all random I/O is now serviced out of the persistent memory. We reduced the DRAM in the system roughly by 30x and allocated only for hot indices. And in the software tiers now, since we don't use that anymore, we don't need the page and block caches, which we turned off, and essentially now accessing storage mainly for checkpointing from main persistent memory into the storage tier. That allowed us to design the storage quite differently. Now we are disaggregating storage, and what we do in our storage nodes are our Intel ruler-based QLC SSDs, and we're disaggregating these SSDs over an NVMe over Fabric network and using RDMA into them. And as I mentioned before, the accesses to the storage tier are going to be mostly sequential. So we're essentially using this tier as not an IOPS tier, but a bandwidth tier. And we also use an integrated cloud storage API S3 for this tier. And the whole thing is built and interconnected with 100 gig Ethernet and Kubernetes orchestrated. So I want to show you how this whole thing comes together in a small movie we put together. So if you could please roll that movie for us real quickly.
Intel's Optane DC persistent memory and storage innovations will transform big data workloads and analytics possibilities in the data center. Data will be able to be stored, moved, and processed at unprecedented speed with improved TCO. New media technology removes much of the latency associated with memory and storage based on traditional media, bringing needed data closer to the processor. As data continues to grow rapidly, the need for high-performance, high-density storage is critical. Intel's goal is to replace hard drives with fast, high-capacity NVMe SSDs, leveraging our ultra-dense QLC NAND technology. Our ultra-dense ruler SSD form factor is gaining traction with thermal, operational, and space efficiency, enabling us to pack up to 1 petabyte of storage in a single 1U box. Future designs will consist of disaggregated compute, storage, and network pools that can be dynamically provisioned on demand. Intel Optane DC persistent memory, Intel Optane DC SSDs, and QLC NAND SSDs will provide fast, high-capacity, cost-effective memory and storage. But these disaggregated pools require a next-gen network design to maximize performance, which is where NVMe over Fabric comes in. New standards and next-gen fabrics enable us to make remote NVMe storage appear to be local, speeding data to compute nodes while enabling compute and storage to scale independently. These combined innovations, fast, high-capacity persistent memory and storage traveling across high-speed NVMe over Fabric links, will enable new levels of performance and reduce TCO in the data center.
All right, so I promise this is the only marketing material I'll use. So back to our data management platform. So what I wanted to do is, now that you know what it looks like and how we built it, I want to put this entire solution back into the framework we discussed earlier. So in that framework, what we have done here is 3 main things. First of all, the main memory tier, the performance tier, we used persistent memory. That allowed us to significantly reduce the overall cost compared to a DRAM-based solution. Next, we have reduced the amount of DRAM in the system by about 30x and limited it to only fast, hot indices. And by essentially removing all the random I/O from the storage stack and sequentializing it, we were able to push the entire storage tier into a disaggregated, low-cost, high-capacity tier that's connected through an NVMe over Fabric. So you put all these 3 different things, and now you can think how you could, or one could, rethink all these different technologies that we have available to us coming together all around persistent memory. So this is one idea we have. We're working on that. But I'm sure that you, the many brilliant people in this room, are going to have many more of these brilliant ideas. So in concluding my presentation, I'm inviting you to please join the persistent memory. Please bring your wonderful ideas, and let's collaborate together. And please join this wonderful list of revolutionaries on our path with us. So thank you all so much, and look forward to seeing you all very soon. Thank you.